We're going to start looking at Chapter 9. Our first section just deals with investigating mathematical patterns. Our objectives today will be to identify mathematical patterns found in a sequence and use a formula to find the nth term of a sequence. If the numbers in a list follow a pattern, you may be able to relate each number in the list to its numerical position in the list with a rule or some kind of formula. A sequence is an ordered list of numbers. Each number in a sequence is called a term of the sequence. You can represent a term of a sequence by using a variable with a subscript number to indicate its position in the sequence. For example, a with a little subscript of 5, we read that a sub 5, is the fifth term of the sequence a sub 1, a sub 2, a sub 3, a sub 4, etc. The subscripts of a sequence terms are often positive integers starting with a 1. If so, you can generalize a term as a sub n, which would represent the nth term of a sequence. So our first term here would be a sub 1. Second term is a sub 2, and we're going to keep going until we get to the nth term. Now notice our number for subscripts keep going up by 1. So if we're at position n here, up by 1, our next term in the list would be a sub n plus 1, which means the number in front would have 1 less for its n value. And you're going to see this notation in some of our formulas. I want you to think of it as the previous term. So if we're looking for the nth term, a sub n minus 1 would be the previous number in our list. Now we have two types of formulas. We have explicit and recursive. We're going to start with an explicit formula. It describes the nth term of a sequence using the position number n. All right, so for example, in the sequence 2, 4, 6, 8, 10, etc., the nth term is just twice the value of n. If you think about the position, this would be our first term, second term, third term, fourth term, fifth term. So all we're doing is we're taking this n value and multiplying by 2 to get the actual number in our list. So we have a formula, a sub n is just twice the position it's in. And the table shows you how those were calculated. So first term is 2 times 1, second term 2 times 2, third term 2 times 3, etc. To generate a sequence using an explicit formula. If the formula is already given to you, like we have in this example, a sub n equals 3 times n minus 2. It's asking us to write out the first 10 numbers in our sequence. So a sub 1 means our n value is 1. We're going to have 3 times 1 minus 2, and that gets us a 1. A sub 2 is going to be 3 times its position of 2, the second term in our list, minus 2. So we have 6 minus 2 would be 4. A sub 3 is going to be the third number in our list. So we have 9 minus 2 or 7. A sub 4 would be 3 times 4 minus 2. 12 minus 2 would be 10. A sub 5, 3 times 5 minus 2. 15 minus 2 would be 13. A sub 6, we've got 18 minus 2, or 16. A sub 7, and we're going to keep doing the same pattern until we get the first 10 numbers. What do we have, 22? A sub 9 would be 3 times 9 minus 2. So 27 minus 2 would be 25. And our last number, 3 times 10 minus 2, would be 28. So if we had to generate that list of the first 10 numbers, our numbers would be 1, 4, 7, 10, 13, 16, 19, 22, 25, and 28. Sometimes you can see the pattern in a sequence by comparing each term to the one that came before it. For example, in the sequence 133, 130, 127, 124, etc., each term after that first term is just 3 less than the previous number. So in other words, we're just subtracting 3 each time. When we look at how it relates, how a number in a list relates to the previous term, we are looking at something called a recursive definition or a recursive rule. A recursive rule has to have 2 parts. The first part is an initial condition. In other words, you have to state what the first number in your list is. The second part of it is that you then give a recursive rule or formula that relates each term after the first one to the one that came before it. So in our list, we said the first number in that example was 133, and we said that we're going to keep subtracting 3 from that. So we are subtracting 3 from the previous term. All right, so if I want to find the nth term, the n minus 1th term would be the one that would be right in front of that. So if I were going to generate this list, I'm going to say my first term is 133. My second term is found by taking the previous number and subtracting 3. Then my next term is going to take the previous number, the 130, and subtract 3 to get 127. Then I'm going to take the previous answer, 127, subtract 3 to get 124. And I could keep generating the list that way. A recursive rule for our example here. We have a list of numbers, 1, 2, 6, 24, 120, and 720. We are trying to write a recursive rule. So we have to somehow figure out how each term is related to the one in front of it. So if we look at our list here, our first number is 1. We multiply by 2 and get 2. Our next number, we have to multiply by 3 to go from 2 to 6. 6 times 4 gets us 24. 24 times 5 gets us 120. And 120 times 6 would get us 720. So you'll notice that it is a multiplication pattern, but what we're multiplying by keeps changing. Now, I want you to consider the position each of these numbers is in terms of my list. That's my first term, second term, third term, fourth term, fifth term, sixth term. So notice that to get, for example, this 720, I took the previous answer and I multiplied by the number that was the n value. Okay? The same thing could be said if I keep working back. To get to the 24, I took the previous number 6, multiplied it by its n value, and got the 24. So I can state recursively my recursive definition. I always have to say how my list starts. My first term in this case is a 1, the very first number in my list. Then every number after that, I'm going to take the previous number, the previous term, and I'm going to multiply it by the position I want it to be in. And this is true for all n values bigger than 1. So this is when n is 1. I've stated the initial condition, and this is the rule I'm going to use for everything after that. All right, let's look at another one that we're still going to write recursively. We have 1, 5, 14, 30, 55. Again, if we think of the position those numbers are in, all right, we've got 1, 5, 14, 30, 55. In this case, it's an addition pattern. My first number here, to go from 1 to 5, I added 4. To go from 5 to 14, I added 9. To go from 14 to 30, I added 16. And to go from 30 to 55, I added 25. So similar to our previous example where we were using our n value somehow in our formula. In this case, we're not just using n, what are we doing to it? What am I doing to 5 to get to 25? with 4 to turn it into a 16, with a 3 to turn it into a 9. I'm just squaring it. So my formula says identify your first term, and then recursive formula would say the nth term is going to take the previous number, so my previous answer, I'm adding to it the square of the position that it's in. Okay, so if I wanted to continue this pattern to get to my 6th term, I'm going to have to take 55 and add 6 squared, or add 36 to it. And we end up with 91 would be our 6th term. All right, recursive definitions are helpful on the small scale because you're always relating it to the previous number. But if I'm looking, say, for the 5,000th term in my list, I don't want a recursive rule. That would mean I'd have to generate 4,999 other numbers before I can get to the 5,000th number. So in that case, an explicit formula would be much more useful. So we're going to go back to that same example and look at how we could write it with an explicit formula. Now, an explicit formula simply relates it to its position. It doesn't relate it to the previous number. All right, so you may recognize these numbers, you may not. 1, 2, 6, 24, 120, 720. That is a special pattern. Let's break it down. The first term of 1 is just 1 times itself. The second term is 2 times 1. My third number, the 6, is 3 times 2 times 1. To get 24, I'm taking 4 times 3 times 2 times 1. 120, 5 times 4 times 3 times 2 times 1. And 720, 6 times 5 times 4 times 3 times 2 times 1. Those are what we call factorials. So my first number here is just 1 factorial. 2 times 1 is 2 factorial. 3 times 2 times 1 is 3 factorial. And it keeps going. 4 factorial, 5 factorial, 6 factorial. Okay? So to get a number in the list, we are taking the position it's in, 1, 2, 3, 4, 5, 6, etc., and we're using that factorial. So I simply state my nth term is going to be n factorial. All right, our next example, again, if we are writing an explicit rule, we have to relate it to the position the number's in. Okay? Looking at the numbers 0, 3, 8, 15, 24. The pattern that I see here is I'm almost at n squared. If I list my perfect squares, I have 1, 4, 9, 16, 25, etc. Well, these numbers are just 1 less than that. So my rule would be I'm going to take my n value and square it, and then I'm just going to reduce it by 1. Now, many of these patterns aren't the easiest to see when you first look at it. Look for things, maybe it's a common number that you're adding each time, or a common number that you're multiplying by each time. In the cases we had here, we looked at some factorials, we looked at some squaring patterns. Don't panic if you're not seeing the patterns right away. As we continue on in this chapter, we get to some very specific type of explicit rules that might make it a little easier for you. Our last example, we're going to look at a word problem. It says Pierre began the year with an unpaid balance of $300 on his credit card. Because he had not read the credit card agreement, he did not realize that the company is charging 1.8% interest each month on his unpaid balance, in addition to a $29 penalty in any month that he might fail to make a minimum payment. Pierre ignored his credit card bill for 4 consecutive months before finally deciding to pay off the balance. What did he owe after 4 months of non-payment? So there is a pattern to this. We can set it up as a sequence. Our starting value is $300. Now, this is before he even started looking for paying things off each month. So I'm going to call that A sub 0. That's the amount before we even get our first bill. Okay, now, what is happening to that unpaid balance? In any given month, we are going to take the previous amount, so the balance that I haven't paid off, we are going to multiply it by an extra 1.8%. So we are going to take the previous month's bill that we haven't paid, we are going to multiply it by the total bill plus an extra 1.8%. So that would be the number 1.018. So the initial 1 here gets my initial value of $300, and it's going to charge me the extra 1.8% on top of that. Plus, I have to pay a $29 penalty since I didn't make a payment that month. So let's look at what happens if I don't pay my bill. The first month that I don't pay my bill, I am spending 1.018 times that $300 that I didn't pay off, plus an extra $29. Grab your calculators, multiply that out, add your 29. We should get $334.40. So the first month that I don't pay it, I am getting charged an extra $34.40. My next month, I am paying that extra 1.8% interest on the previous month's bill, and I still haven't paid it off. Now they're saying I owe this much plus the extra $29 fee. Again, with our calculators, that total comes out to be $369.42. Okay, still don't make a payment. So month 3 rolls around. I am now paying an extra 1.8% interest on the $369.42 that I've added up to here, plus my $29 in a late fee, and now I am at $405.07. My fourth bill comes in the mail. They are charging me an extra 1.8% of my $405.07 that I haven't paid off, plus my $29 late fee. And so now when I go to pay it off, I actually owe $441.36. So my initial charge was $300, but I haven't paid it for 3 months, so I kept getting this interest payment plus a late fee payment, and now I owe $441.36. So an extra $141 just because I didn't pay it off. All right, so again, today's topic, we were looking at, can you identify a pattern found in a sequence, and look at how we can write formulas to find the nth term. Now remember, there are 2 types. We have explicit, where we relate it to our n, our position number, and we have recursive, where we state, here's my first term, and then all my other numbers are going to somehow be related to that previous term, and maybe we're adding or multiplying by something else. All right, so homework assignment is listed here.